Question 1. Which of the following particles never acts like a charge carrier? Now remember, a charge carrier is any charged particle that is free to move. If it can move, then it can carry charge and cause an electric current. So our options are a positive ion, a negative ion, an electron, or an atom. Now, what's the difference between an ion and an atom? Well, an ion simply has a charge, otherwise it's identical to an atom. So a positive ion has a positive charge, a negative ion has a negative charge, an electron has a negative charge, and an atom has no charge, because otherwise it would be called an ion. So the atom, because it has no charge, cannot be a charge carrier. All of these other ones can carry charge by moving. Electron can move through a metal wire freely, and positive and negative ions can flow through salty water. So the atom is the only one without a net electric charge, and so the only one that cannot carry a current. Question 2. Which of the following devices can measure electric current? Is it a voltmeter, ammeter, electrometer, or a galvanic cell? Now all of these, except the galvanic cell, are used to measure something, but only one of them is used to measure current. Let's go through them. A voltmeter, as you might expect, measures voltage. An electrometer measures electric charge. A galvanic cell is a type of battery. You might come across it in chemistry. And finally, an ammeter is what we use to measure electric current. So B is the correct answer. Question 3. During a lightning strike, a current of 30,000 amperes, a very large current indeed, flows between a cloud and the ground for 0.4 milliseconds. That is 0.4 thousandths of a second. How much charge is transmitted by the bolt of lightning? Now let's work this out. What's the equation that we use to calculate charge in terms of current? Q equals I delta T. Can you see how we got this? All we needed to do was rearrange the equation for current. Current equals change in charge over the change in time. Multiplying both sides by delta T gives us the equation that we use here. So all we need to do is substitute in the values. For I, we substitute in 30,000 amps, and for delta T, we substitute in 0.00004, a very small number indeed, because it's less than a thousandth of a second. So substituting these in, we end up with an answer of 12 coulombs, quite a large amount of electric charge, as you might imagine if it's transmitted by a bolt of lightning. Question 4. In a certain wire, 2 billion electrons going left to right pass a given cross-section of wire every microsecond. That is, every 10 to the minus 6 seconds. Find the current in the wire. Now remember, if the electrons are going left to right, that's the direction that the negative charge is moving in. In physics, we often talk about the direction that the positive charges are moving in, even if there are no positive charges that are actually moving. It means that if we have negative particles moving in this direction, what we call the conventional current goes in the other direction, right? So the direction of the electric current will be going right to left instead of left to right. Now that we've got that out of the way, let's answer the rest of the question. We know the number of electrons passing through the cross-sectional wire, and we know the amount of time in which they do it. What we need then is this equation. Current equals change in charge over the change in time. But how do we find the change in charge? Well, what we do is we multiply the charge of the electron by the number of electrons, and that gives us the total charge moving through the cross-section. Makes sense, right? So, substituting those in, we end up with an answer of minus 3.2 times 10 to the minus 4 amps. Now, this minus shows us the direction of the current from left to right, the same direction as the electrons. So if we want to find the current as a positive number, we'll have to go back the other way, right to left. Of course, we can express 3.2 times 10 to the minus 4 amps as 0.32 milliamps. That is a third of a thousandth of an amp. So the current in the wire is minus 0.32 milliamps left to right, which is the same as positive 0.32 milliamps right to left. Question 5. A school student conducts an experiment to calculate the current flowing in a small, low-power electric circuit in the lab. After doing some calculations, he determines that the current in the circuit is 25 amps. Is this a reasonable figure? Explain why or why not. Now, being able to answer a question like this is a very useful skill if you ever want to do experimental work in the lab. So, what do you think? Is 25 amps reasonable? Is it too large or too small? Well, it's probably far too large. This is not a very reasonable figure. Even if we had 10 amps, we'd be getting a very large amount of energy being output from the circuit. And so it certainly wouldn't be classified as a small, low-power electric circuit. Remember that 1 amp is already a high amount of current, and 5 amps is able to produce a large amount of light or heat energy. Remember that a car's headlight uses less than 5 amps to produce all that brightness. So if we were to measure a low-power circuit and get 25 amps, then there's probably something wrong with our measurement or our calculations. The current in the student's circuit is more likely to be perhaps 0.25 amps, or maybe even 25 milliamps. This might be likely because it's possible to calibrate the ammeter so that instead of measuring in amps, it might be measuring in milliamps, and that would explain why he's off by so much. Question 6. When electric current flows through salty water, it is carried by positively charged and negatively charged ions. Do the two types of ion move in the same direction? Justify your answer. Now, to answer this, we're going to have to think about what causes an electric current. Remember that if we have an electric current, we have a movement of charged particles. To form a movement of charged particles, we need them to be attracted or repelled from a particular charge. So suppose that to create a current, we put a big negatively charged plate here and a big positively charged plate here. Now, if we put a charged particle in between them, it'll be attracted to one of them, which means we will have electric current. Now, suppose we're in this situation and we have positively charged ions and negatively charged ions. So we have positive charges and negative charges. The negative charges will be attracted this way and repelled this way, but the positive charges will move in the opposite direction. So, are they going to move in the same direction? Well, certainly not. You can see that they're going to move in quite the opposite direction. The positive charge will move in the direction that we expect the conventional current to flow in, and the negative charge will move in the opposite direction. When an electric current flows, it is caused by an electric field generated by a power supply. Positive and negative charges move in opposite directions if they're placed in the same electric field. And this means that the two types of ions will move in opposite directions in order to carry the current in the same direction. So that's the end of the questions. In this section, we've learned about electric current. We've learned about the charge carriers that carry electric current in various different conductors, and we've learned about what sort of numbers we might expect to see in various electrical circuits. Now, these numbers can be quite helpful. If you get a number that seems quite off, don't forget to check you're working out.